SwayamPrabha. Digital India. Educated India.
So, in this lecture we are going to talk about ordering kinetics basically, and few important microstructural features. As you said, as you have seen in the last lecture, I talked about different type of order structures, and I talked about thermodynamics of ordering, how we can differentiate first order, second order transformations, and we can correlate these ordering transformations whether it is a continuous or discontinuous type. But before I go into the microstructural features and as well as ordering kinetics, let me tell you that if I consider simple BCC structure, you know that corner atoms and the body center atoms are average type. So, you have only one kind of a lattice structure, but the moment it becomes order B2, we cannot no longer have only one type of lattices. We need to define lattices specific to the atoms. So, simply all the corner atoms are here occupied by the Rn in a PEL structure. So, that means if I have a large number of unit cells together, I can always define a simple cubic structure in which all the corner atoms are occupied by the Rn. Similarly, if I draw many unit cells, okay, then I can actually connect these central atoms, all the central atoms which are occupied by aluminum, and then I can actually have another type of a lattice structure where basically atoms are occupied by the aluminum atoms only. So, what I mean to say is that in order structure we can define sub lattices. One sub lattice is occupied predominantly by the Rn atoms or only by the Rn atoms in a B2 structure, other sub lattice is occupied by only by the aluminum atoms. So, that means in B2 structure is nothing but a two interpenetrating BCC unit cells, simple cubic unit cells, one occupied by the iron atoms, other one occupied by the aluminum atoms. You can actually think of that way always. So, once you have that kind of structures, we can actually extend this one to other structures, like in case of L12 structures we can think of 4 different sublattices. One sublattice is occupied by the gold atoms, which is corner atoms of the FCC unit cells, and other 3 sublattices are basically occupied by the copper. We can only consider 2 atoms in the face center positions in the unit cells, and if we draw a large number of unit cells, we can connect them and get a face center simple cubic structure that way. So, this is nothing but a 4 simple cubic sublattices occupied by the gold and 1 gold type and other 3 copper type sublattices. So, that can be always done for any structure. If that is the case, then how actually ordering happens? Well, let us consider a situation like that. Ordering process taking place inside a grain in many places. When the ordering happens from this sort of structure, from alpha to L12 structure, whenever it develops, in a grain it can happen in many, just like a nucleation process, many places, okay, like that. So, these are actually order phases which have started nucleating inside a grain. If that is what happens, now once these ordered regions grow from different parts of the grain, they will meet each other, okay. And when they meet, what kind of atomic arrangements will happen? That can be easily explained by looking at these kind of sublattices. Let us consider that these closed atoms are actually again gold, and the closed atom are basically copper, and these open atoms are actually gold. So, you can see here I have superimposed a 2-dimensional projections of the gold sublattice and the copper sublattice, okay. And obviously they are displaced because the copper atoms are sitting at the face center positions and gold atoms are sitting at the corner positions, okay. So, we can actually displace one sublattice with respect to other sublattice by half A, basically A by 2 1 1 0. That is the normal situation. So, if one part of the grain the crystal was, or the order crystal was going with such a kind of arrangements, and other part of the grain it was going in another way, that is the corner atoms are occupied with the gold and these phase center positions are occupied by the copper. Okay, now phase center atoms are occupied by the gold, corner atoms are occupied by the copper, and if they grow and once they meet, and a boundary will form in which the bonds will be similar types. You can see here bonds are basically dissimilar types. A copper has a bond with gold or vice versa, gold has a bond with copper. You can see here all the bonds are like that, nearest neighbors. But and here also on this side also exactly same. This is a gold atom, it has bonds with copper. Similarly, if I take a copper atom, it has a bond with gold, all the bonds are gold. So opposite type of bonds are happening in the both sides, okay, whether it is a gold copper or copper gold. But the moment these two domains actually, or these two order regions meet along this boundary, the bonds are actually similar types. You can see there, okay, copper copper, gold gold, copper copper, gold gold, copper copper, gold gold. So that means what? There is a bonding change across these meeting boundary, and that is why this meeting boundary is known as anti-phase domain boundary, because this is demarcating a change in the atomic structure, change in the atomic bonding structure, I would say, and that actually is a very important aspect. So how we can define crystallographically? Crystallographically, this can be defined as an atomic displacement. Remember at the beginning I talked about the displacement of these phase center copper atoms from the corner gold atoms by A by 2 1 1 0. Okay. So similarly we can actually talk about antiphase domain as a boundary, as a displacement of the atomic positions. How we can do that? You can very easily see this copper gold atom which is sitting here should have been a copper atom, then the bonding could have been opposite, or this copper atom should have been a gold atom, then this bonding had been copper. That has not happened. So therefore displacement can be talked about atomic displacement. It seems here crystallographically atomic displacement will be A by 2, basically 1 bar 1 1, okay, and this happens mostly on 110 planes, okay. That's can be seen from the crystal structure. 110 planes are actually, that's why the displacement is happening. Which are the 110 planes here? Let us go back to the crystal structure here, okay. So you see 110 plane is what? 110 plane is, this is one of the 110 plane, okay. So that means what? This displacement, so therefore if I draw a body center things which is 111 directions, body diagonal basically, so half on this plane, half 111 displacement means one atom going from here to the central atom is what is known as, this is basically half 110 here. So the one which I was talking is basically for B2 structure. For B2 structure basically body center cubic, body diagonal is this one, so and this is 110 planes. So along the 110 plane if I displace one atom from here to there is become A by 2 111 or 1 bar 1 1, okay. So that displacement is equivalent to displacing the atoms here, what is shown here, displacing the atoms like that way. When in a obviously in a CU3 AU structure it will be 110, not 111. So half 111 along 111 plane basically is what is the displacement vector. So these displacement vectors are well known, whether it is a FCC, BCC or a hexagon structure, the displacement vectors are well known along the antiphase domain boundaries, and this can be defined in a very specific manner by knowing the crystal structures. Whatever the situations, it is very clear to you antiphase domain boundary is nothing but a boundary along which bonds actually similar atoms, bonds between similar atoms forms. It is not the bond between these similar atoms which stabilizes the order structure prevalent along the antiphase domain boundary, it is the bond between the similar atoms which is prevalent. So now we can, by knowing that we can actually image that in a crystal structure. Now before actually I go into those big structure, let me tell you that how actually things happens in a better way. This is again directly taken from the book of the Porter and Sterling. You see here these are the two order domains which is formed inside one grain. One was this type in which the gold atoms are actually sitting at these positions and copper atoms sitting at these positions. Another one is opposite, gold atoms are sitting, no, all other ones also similar. So, when they are actually growing together, you see there is a boundary forms. Okay. So, that boundary basically tells you that bonds are of similar types, and this finally can become bigger and lead to APV or antiphase domain boundaries, which is shown there. And this diagram represents the atomic positions along one OO plane, that is why it is shown like this. One OO plane is the top plane or the bottom planes or the side planes, whatever it is. If I draw it properly, it will be clear to you. So, these are the gold atoms and these are the copper atoms, all the phase center positions. Okay. So, this is 11001 plane type, or this is actually 100 types. You can clearly see that this has corner atoms are occupied by the either gold or copper. Basically, this is AU Cu3 AU, that is why it is occupied by, okay, please forgive me, here actually this is copper and this is gold, because these are taken from two different books, that is why the symbols are different. So, as you clearly see here, when they meet, there is opposite type of bond formation. That is very important to observe, not the how things are arranged. Now, one can actually look at in a B2 structure, exactly similar way, along the boundaries similar type of bonds are forming, along the boundaries similar type of bonds are formed. Okay. So, that is why it is basically tells you, tell you that these are actually boundaries. Okay. You can see here similar type of bonds are formed. Everywhere, and this can be imaged in a microscope, mostly in a transmission electron microscopes, as a boundary like this, which actually tells you the antiphase domains. Okay. And this is the boundary and these are actually domains, order domains. Remember, this also happens in magnetic materials. Many of the magnetic materials are order structures, and there these domains actually are equivalent to magnetic domains. In a case of a Cu3 AU, they look like such a kind of structure. You can see the antiphase domain boundaries looks like a Zagat structure. So, across these boundaries atomic bonding is similar atom type. Within the boundaries, within these domains, these similar types bonds are preferred. That is a major difference between the order and the disorder structures. Okay. And because ordering is basically will happen by nucleation and growth process, that means inside a grain some parts of the grain will start forming order structures and then they will grow and become a disorder structures, and that is why these domain boundaries are prevalently observed in the microstructures, which is very common in any order structures. Anything which is ordering in a solid state will have such a kind of domain boundaries present along these in these microstructures, which is observed specifically that. Now, one can actually look at much better way how actually ordering kinetic happens. That means how actually ordering takes place, in the sense that atomically how these domains actually coming together and becoming bigger. That is a little difficult to conceive at the stage or to understand at the stage you are in, because atomic arrangements what I have shown you here is a much simpler one. But in a real picture, real sense, if I have a large grain and we have domains forming, small domains forming inside these grains, how these domains actually are moving, because the growth of the domains require the bonding change. Okay. Within this domain you have dissimilar bonds, but outside that you can have average bonds. So, once this one grows, that means the bonding characteristics of this region to which it has grown will become also dissimilar bonds. Okay. So, that can only be possible once the bonds are broken, bonds between similar atoms are broken, and then bonds between dissimilar atoms forms. So, virtually the important aspect for you to understand is that this bonding characteristics change from similar to dissimilar requires bond broken and forming again, and that is not actually very simple way we can explain in a course like this. This happens in a much complex way. It does not happen that bond between two similar atoms gets broken immediately, and then that open bond forms between dissimilar atoms. That is not the way it happens. What I am going to tell you, it happens much complex way. There are a lot of integration involved. Let us not discuss about that. So next, the last thing which I would like to talk is that even in case of gold copper structure, in case of AuCu structure rather, the one which I showed you, which is L10 structure, as you clearly see here, this is the unit cell is longer, much longer. Why? Because here the atoms which are joined, or the unit cells which have joined, remember that this is the simple unit cell, FCC unit cell, which is a disorder structure. Again there is a order structure, there is a reversal, and then there is again a reversal here. You can see here there is a reversal here. This happens more frequently in case of AuCu structure, which is a L10 structure. It has been observed, not like other one L12, which is a Cu3Au structure, or AuCu structure, all B2 structure like copper, zinc, or iron, aluminum. And the shift which has been shown here, half A per C on 010 planes, that leads to such a kind of antiphase domains in this structure is unique. It is not present in the other structures. And such things has been observed because displacement has been observed in the microstructure of these phases, which is also cannot be discussed in a detailed manner because this requires me to go back to the crystallography of these. Anyway, what you need to understand is basically that in case of gold copper 50-50 alloy, such a complex ordering happens. In that case 1, 2, 3, 4, 5 unit cells join together and form a supercell, and this supercell actually has a lattice parameter AB which is same, but C has a very large lattice parameter, and that is why it has become a L10 structure, which is known as a order tetragonal structure. That is the reason it forms such a kind of structures. Okay, with this let us stop about the order disorder transformations, and we'll discuss in the next the recovery recrystallization structures which form the transformations which are present in many of the deformed structure in the next, and try to discuss with you many interesting phenomena there. Okay.